Section 9.1.4 brings us to sums and series. So a series is, let's start an example again like we did last couple times. That worked out okay. So an example we have of a sequence. So we talked about what a sequence is in the first section. So an example of a sequence here would be 2, 4, 6, 8, and you probably recognize this sequence. And could even say that the nth term is 2n, 2 times n. So a series is a sum of the numbers in the sequence. So for example, if I try to take the sum of this sequence of 2n, I wouldn't be able to because it goes on for infinity. The numbers keep getting bigger and bigger. So I would never be able to add it all together because the numbers never end and they keep getting bigger and bigger. So it'd just be infinity. But I could take a partial sum. So let's look at our definition here. So given an infinite sequence, we have an infinite sequence here that we kind of made up. The sum of all the terms in the infinite sequence is called an infinite series and is denoted by this. And the sum of the first n terms is called a finite series or an nth partial sum. So we're going to find, let's do the fourth partial sum. So that means we take the first, let's do the fifth partial sum. So we add one more to what we have here. So we take the first 5 numbers of the sequence and add them together. So the fifth partial sum is the first 5 elements of this sequence, which is 2 plus 4 plus 6 plus 8, and that fifth term would be 10 following that pattern. And that sum is, let's see, I have 10 plus 10 more plus 10 more, so that gives me 30. So my partial sum, my fifth partial sum, is 30 for this sequence. So that is a finite series. We also have some abbreviation for sum. We have the capital Greek letter sigma, and actually it's not even just a capital Greek, it's actually an oversized Greek letter. So sigma is a regular Greek letter, but when we use it to represent the mathematical sum operation, we oversize it. So it's a really big sum, really big sigma. So anyway, that letter tells us it's sigma, S for sum. Therefore, we use sigma as a shorthand way to represent a sum or a series. So a sum of a sequence, or a sum of certain number of elements of a sequence, is called a series. So for example, the sum of the first 5 terms of the sequence 1, 4, 9, 16, 25, n squared, can be represented by using sigma notation. The number under the sigma tells me which element to start with. Remember, this is the first term, second term, third term, element, I guess, fourth element, fifth element, and then we go all the way up to 5. So where we start, or I say which term we start on, which term we end on. And then we use the sum of this formula. So if I have n going from 1 to 5, I have 5 spaces to fill. And then in each one of those spaces, I have n squared. So when n equals 1, we have 1 squared. When n equals 2, we have 2 squared. When n equals 3, we have 3 squared. When n equals 4, we have 4 squared. When n equals 5, we have 5 squared. And when n equals 6, we're actually already done because we stopped at 5. So this is read as the sum as n goes from 1 to 5 of n squared. So the letter n is called the index of summation, and often other letters are used instead of n, like j and k are common ones. It's important to note that the sum can start at any number besides 1. It could start at 0, it could start at 15. If we wanted the sum of all the terms in a sequence, we use the infinity on top to say just keep adding And that would look like that. Okay, so let's talk about our study tips here. We talked about that oversized sigma already. We can also, so I said what we start at, we put on the bottom, and then what we end on, we put on top. You might also see it like this, or you might even see it like this, where it's obvious what the variable is. Like as in when you see your equation, say n squared, for example, it'd be obvious that the only variable there is the one I plug in my 1 for. A series can start at any integer, not just one, and the sum of a finite series always exists. So if I have just a sum of the first 5, for example, 1 through 5, I'll be able to add up those 5 numbers just by adding them. But the sum of an infinite series, like this guy, does not always exist. Like if I try to add up all those numbers, the numbers just continually get bigger, so I never really get to a number. I just get to infinity, so it does not exist. But sometimes it does exist. Like for example, when I have an alternating series, like -1, +1, -2, +2. So sometimes it does exist. But a finite series will always exist. All right, so let's move on to your homework problems. So we're looking in the first section, we have 51 through 64, and we want to evaluate these series. I have 2 examples here that are similar to these problems. So this one, I have n going from 1 to 4 of 3. So we're looking for the sum as n goes from 1 to 4 of 3. Okay, so remember when I said if I have a n going from 1 to 4, I should have 4 blanks of things to add together. 1, 2, 3, 4. So when I plug in n equal 1, well, 3 equals 3. When I plug in n equals 2, well, 3 still equals 3. When I plug in n equals 3, yep, 3 still equals 3. And when I plug in n equals 4, 3 still equals 3. So even though I plug in a 3 for each one of these, there's still 3, because it's just a constant. But I still have to add it 4 times because my sum says to add from 1 to, for n equal to 1, n equal to 2, n equal to 3, and n equal to 4. So I add that 4 times together, and I get 3 times 4, which is 12. Okay, moving on to example 2. Here I have a sum of all the terms as n goes from 0 to 3. Remember, we don't always have to start at 1. We can start at 0 too. So n goes from 0 to 3 of n squared. So I have 0, 1, 2, and 3. So those are my possible n values. N equals 0, n equals 1, n equals 2, n equals 3. And I'm going to add them together. And I get, let's see, when n equals 0, n squared is 0. When n equals 1, n squared is 1. When n equals 2, n squared is 4. And when n equals 3, n squared is 9. So adding those together, I get 14. And with that example, that brings me to an example from your book I'd like you to go watch. That is on, let's see, what page are we on here? This is on page 699. And if you can go pause this video, go watch that example, and then come back here to do one together. Okay, so if you tried that example, you watched that example, go ahead and turn to your homework and try, well, not to your homework, to these 2 examples, and see if you can solve or apply segment notation to these 2 sums. Go ahead and pause this video and write those 2 sums. Okay, let's see how you did. Sorry. Okay, so for this one, we actually have an alternating positive, negative, positive, negative. So I'm going to have a sum. Let's see, I have 1, 2, 3, 4, 5 terms. So let's try going from, I don't know, n equals 1 to 5, and let's see if that works. And I want my first term to be positive and my second term to be negative. So that means I would take a negative 1, and if I want the first term to be positive, then I want to add 1 to n. So that ends up being an even exponent, and I get a positive in front. And that will give me an alternating negative 1 starting with when n equals 1, it would be positive. And then I think, okay, so now how do I get that fraction? Actually, I'm going to scoot my sum down a little bit so I can think about these n values. So here, n equals 1, n equals 2, n equals 3. It's hard to find a relationship between the 2 to 3 and the 3 to the 9, but I do see something else that might work. If I actually start with n equals 0 instead of 1, then I have each one of these, I'm multiplying the numerator by 3 and multiplying by 1/3 each time. So each one of these is a power of 3. So I'm actually going to change that exponent since I'm now starting at n equals 0. Now I move that to n equals 0, and I still want that first term to be positive. So negative 1 to the 0 gives me a 1. And then for my fraction, I could take 1 over, remember the 3, the 9, the 27, the 81, and I can think of this as a 1. Then these are each a power of 1 starting at 3 to the power of 0. And then I have 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, 3 to the power of 4. So there's a formula that's starting at 0, but I only have 5 terms, so that means instead of going all the way to 5, I'll just go to 4. So I have n going from 0 to 4. The sum of n going from 0 to 4 of negative 1 to the n times 1 over 3 to the n. So looking for some patterns, I found that I needed to start with 0 in order to get that 1 out in front. And I found I need a negative 1 to a power, so I can alternate positive, negative, positive, negative. And I looked at the numbers, those fractions, and I said, okay, well, what do those numbers have in common with the n? They are all multiplying by 3. They're all powers of 3. So that gives me this solution. Okay, now to the next one. For example 2, I again see I have an alternating plus, minus, so I know I'm going to need a negative 1. This time I think I'm going to find my n's before I make my sigma, because that you saw before I had to change my n's. So let's see. If I plug in 1 here, and I plug in a 2 here, plug in a 3 here, n equal 4 here. These are, it looks like they're all squares of n. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. I do have to keep going though. So I'm going to have to go to infinity. So my sum will go from 1 to infinity. and I'll be alternating. So I have that -1. I want to start with a positive. So I want, when I plug in the 1 for n, I want it the -1's exponent to be even number. So I'll do n plus 1 for my exponent on the -1. So now I will be alternating positive, negative, positive, negative, positive, negative. And then for the value of the number, I have n squared. So there's my series for this sequence. Okay, and that wraps up sums and series for 9.1.4.